Hello everyone and welcome to our notes for section 12.6. Today we're talking about probability using and or. So in example 1, it says find the number of possible outcomes when two cards are drawn from a deck without replacement. So if we use the fundamental counting principle, we're going to have 52 cards to choose from in our first draw. And then since we didn't put that card back in, we're going to have 51 left for the second draw. So we have 52 times 51, meaning we have 2,652 possible outcomes when we draw two cards from a deck of cards. Example 2 says draw a tree diagram of this problem. No. Because this would take a forest. Well, 2,652 is quite a bit of things to write down. So we need something a little bit better than a sample space. And what we're going to talk about today is something called compound probability. And what this does is it lets us solve or and problems involving probability without constructing the sample space. Okay, so we don't need a sample space if we can use compound probability. So we're very excited and we say woohoo. So first off, let's deal with or types of problems. Here's our formula for finding the probability of event A or event B. So we write it, the probability of A or B equals the probability that A occurs plus the probability of event B occurring minus the probability that both A and B happen at the same time. So if A is occurring here and B is occurring here at the same time, we've already included them twice. So we need to subtract the times that they happen at the same time. In example 3, it says find the probability of rolling a die and getting either an even number or a number greater than 4. So what we need to do is find the probability of getting an even number, which would be 3 out of 6. Then we need to find the probability of getting a number greater than 4, which would be 2 out of 6. Then we need to find the probability that you would get an even number and a number greater than 4. Okay, and this is 1 out of 6 because the number 6 is both even and greater than 4. So notice the number 6 would be included here with the evens and also with the greater than 4s. So in our formula, we're going to add together the probability of even plus the probability of greater than 4, and we're going to subtract the probability of both. And so you can just type this into your calculator and get a fraction, reduce 2/3, or 66%. In example 4, it says each of the numbers 1 through 10 is written on a separate piece of paper. The 10 pieces of paper are then placed in a hat, and one piece is randomly selected. It says find the probability that the piece of paper selected contains an even number and a number greater than 6. So let's just use a little Venn diagram here to help us out. So we'll let this be our evens, and we'll let this be greater than 6. So 1 is neither even nor greater than 6, so it'll go outside. 2 is even but not greater than 6. 3, it's not even or greater than 6. 4 is even. 5 is not even and it's not greater than 6. 6 is even but it's not greater than 6. 7 is greater than 6 but it's not even. So that means it's going to go out here. 8 is both even and greater than 6. 9 is greater than 6 but not even. And 10 is both even and greater than 6. So when we look here, everything in the intersection is both even and greater than 6. So here you can see we have 2 items out of our 10 numbers. So we have a 2 in 10 chance, which we can reduce to 1/5 or 20%. Now if we want to answer the question, probability of getting an even number or a number greater than 6, now what we need here is the probability of getting an even plus the probability of getting greater than 6 minus the probability of getting both. So when we look at this, the probability of getting an even number, well, there are 1, 2, 3, 4, 5 even numbers. So that's 5 out of 10. And then the probability of getting a number greater than 6 is 1, 2, 3, 4. So plus 4 out of 10. And then we want to subtract the probability of getting both, which we said was 2 out of 10. Okay, so 5 plus 4 is 9, minus 2 is 7. So we do get 7 out of 10, or 70%. In example 5, we have the same situation with our 10 numbers in a hat. We're still selecting one piece. We want to find the probability that the piece of paper contains a number less than 4 and a number greater than 6. So let's make our new Venn diagram here. Less than 4, greater than 6. So the number 1, 2, and 3 would go here because they're all less than 4, but not greater than 6. 5 and 6 would go outside because they're neither less than 4 nor greater than 6. And then 7, 8, 9, and 10 are all greater than 6, but not less than 4. So we're looking for and here. And remember, and means both. And you can see here we have nothing in our intersection. So the probability of both is going to equal 0 out of 10, meaning it's impossible for a number to be less than 4 as well as greater than 6. So this is just 0%. Now, if we want to find a number less than 4 or a number greater than 6, remember our formula. It's going to be probability of less than 4 plus the probability of greater than 6 plus the probability of both. Okay, so if we want the probability of less than 4, we're going to have a 3 in 10 chance. And then plus the probability of greater than 6, which is a 4 in 10 chance. And then plus the probability of both, which is going to be 0. Okay, because they both don't happen at the same time. So here, we're going to get 7 out of 10, or 70%. Alright, next we want to talk about mutually exclusive events. And it says two events, A and B, are mutually exclusive if it is impossible for both events to occur simultaneously. In other words, the probability of A and B, or both, is 0. So the example that we just had done was an example of mutually exclusive events. Less than 4 and greater than 6. Can't happen. A couple other examples. I win and I lose. I flip a heads and a tail. I draw a club and a red card. So these are mutually exclusive events, meaning they can't happen at the same time. So for example 6, one card is selected from a deck of cards. Determine whether the following pairs of events are mutually exclusive, and then find the probability of A or B. Okay, for letter A, we're looking at an ace and a king. So can an ace card also be a king? Well, in this case, no. So if you answer no to the question, can a card be both, then you're going to say that this is mutually exclusive. So the probability of A or B is just going to be the probability of an ace, which is 4 out of 52, plus the probability of a king, which is 4 out of 52. And then since it's mutually exclusive, there's no chance of it being both. So we're just going to subtract 0. And here we get 8 out of 52, which will reduce to 2 over 13, or 15.4%. Now, if we're looking at an ace and a spade, you ask yourself, can a card be an ace and a spade? Well, the answer is yes. And when you answer yes to that, we say these are not mutually exclusive. So we're going to add the probability of it being an ace plus the probability of it being a spade, and there are 13 spades, and subtracting the probability of it being both. So we have to think, how many aces are also spades? Well, we have the ace of spades. And so there's one card here, so the probability of both is 1 out of 52. So we need to subtract that. And so we have 4 plus 13 minus 1, which is 16 out of 52, which reduces to 4 in 13, which is 30.8%. So next, a red card and a black card. So can a red card also be a black card? Well, the answer is no. So these are mutually exclusive. So the probability of getting a red card is 1/2, and the probability of getting a black card is 1/2, and there's no chance of them being both red and black, so we subtract 0, and so we get 1, or 100%. And it makes sense. If you're drawing a card, is it going to be red or black? Well, it's got to be one of those, so it's going to be 100% every time. How about a picture card or a red card? So can a picture card also be a red card? Well, the answer is yes. So these are not mutually exclusive. Okay, so we're going to need the probability of a picture card, which is 12 out of 52, plus the probability of a red card, which is 26 out of 52, and I'll use this one because it has the same denominator. And then I need to subtract all of the red picture cards. So we have the Jack, Queen, and King of hearts and diamonds. So that equals a total of 6 cards right there. So we're going to subtract 6 out of 52. And this is going to give me 12 plus 26 minus 6 is 32 out of 52, which reduces to 8 in 13, which is 61.5%. Okay, so that is dealing with mutually exclusive events and probability problems using the word or. Now, to start our topic of dealing with and problems, we're going to deal with this question of to replace or not to replace. So with replacement means in an experiment containing more than one trial, each trial would contain the same number of possible outcomes. And this is what we called independent events. Without replacement means in an experiment containing more than one trial, each subsequent trial would contain one less number of possible outcomes. And so you can see here, we have 1/10, 1/9, 1/8, 1/7. Okay, whereas before it stayed the same, 1/10, 1/10, 1/10. Now in without replacement, it's possible that your event you also choose, and so the event could also go down by 1 each time. So without replacement are what we call dependent events. So the formula for finding the probability of event A and event B, assuming that event A has already occurred, is the probability of A times the probability of B. And this is also known as the multiplication formula. So in example 1, it says 2 cards are to be selected with replacement from a deck of cards. Find the probability that 2 aces will be selected. So we need the probability of ace 1 times the probability of a second ace, or ace 2. Okay, so in this example, let's just think about a deck of cards. The probability of the first one being an ace is 4 in 52. Now this is done with replacement. So what we do is we assume we draw our first ace. But then we replace it into the deck. And so we have that ace again as an option. So there are also 4 out of 52 chance for a second ace. And this gives us a 1 in 169 chance, which is about 0.59%. Okay, so now we're going to do the same experiment, but without replacement of the card. So again, we still want the probability of selecting a first ace times the probability of selecting a second ace. So the first ace is still 4 out of 52. So we have to assume that we got that first ace. And now since we don't put it back in the deck, so remember we had our 4 aces, we assume we get one, meaning there are only 3 remaining. So we have 3 out of, well, how many cards are remaining in the deck now? Only 51. And this gives us a probability of 1 in 221, which is about 0.45%. Okay, so notice the chances without replacement are going to be a little bit smaller. So event A and event B are independent events if the occurrence of either event in no way affects the probability of occurrence of the other. So some examples would be rolling dice, tossing a coin. We had another one, roulette. And also now experiments done with replacement. Event A and B are dependent events if the occurrence of event A affects the probability of the occurrence of event B. And for us, this is going to be experiments done without replacement. All right, in example 3, a bowl of jelly beans contains 20 green and 15 orange jelly beans. Samantha, a mathematician, is going to pick and eat 3 jelly beans at random, one after the other. And she's interested in determining the probability that she picks 3 orange jelly beans. So this is for you neurotic people out there, kind of like my wife, who has to eat like one of each color to keep it even. So she would probably eat off 5 green jelly beans first, just to make it an even 15-15. So anyway, this person's interested in getting 3 orange jelly beans in a row. So are the events of picking and eating the jelly beans independent or dependent events in this experiment? Well, what do you think? She's picking and eating the jelly bean. So do you think that's going to affect her chance of picking another jelly bean? Because, you know, I don't think she's going to spit this up. So I would say that these are definitely dependent events. Okay, because one affects the outcome of the next. So let's find the probability that she eats 3 orange jelly beans one after the other. So basically we're going to be looking for the probability of the first one being orange times the probability that the second one's being eaten is orange times the probability of the third one being eaten is orange. So here, the first one being orange, well, there's 15 oranges out of a total of 35 jelly beans, the 20 plus 15. Now, we assume she picks and eats one of these 15, meaning there's only 14 orange ones left, and she ate a jelly bean, so there are now 34 jelly beans. Then we assumed that she picked and ate an orange jelly bean again, so there's only 13 left. And since she ate a jelly bean, there's only 33 left to choose from. So if we multiply these together, we're going to get our total amount. And so this gives us 13 out of 187, which is about 6.95, so 7%. Okay, in example 4, it says a package of 25 citrus tree seeds contains 8 seeds for orange trees, 12 seeds for lemon trees, and 5 seeds for lime trees. 3 seeds are randomly selected and planted, and find the probability of each of the following. So first, that all 3 seeds will produce orange trees. So is this a dependent or independent event? Well, we're actually taking the seed and we're planting it. So we're not putting it back in. So these are dependent events, meaning we're going to have to subtract as we go along. So all 3 seeds will produce orange trees. So we say how many orange trees were there? Well, there were 8. So we have 8 out of 25 total seeds, because there were 25 citrus tree seeds. And then times, we assume we got one, so it's 7 out of 24. And then we assume we get another one, so it's 6 out of 23. And when we multiply this together, we get 14 out of 575, which is about 2.4%. So we have a 2.4% chance that all three seeds are going to be orange trees. So what's the probability that the first seed will produce an orange tree, the second seed will produce a lemon tree, and the third seed will produce an orange tree? So again, these are dependent trials again. So the first seed producing an orange tree is still going to be 8 out of 25. Now here, the second seed has to produce a lemon tree. So we say, how many lemon seeds are still left? Well, we haven't used any, so there are still 12 left. Out of the total possibility, well, how many seeds are still left? Well, because we planted one, there's only 24. Times the probability that the third seed will produce an orange tree. So how many orange seeds are remaining? We used 1, so there are 7. Out of how many seeds are left? Well, we've planted 2 of them, so we're down to 23 seeds. And if we multiply this here, we get 28 out of 575, which is about 4.9%. Okay, so there's a 4.9% chance that the trees will be planted in this order. And what's the probability that none of the seeds will produce an orange tree? Okay, so when we think about this one, the first chance, if it's not orange, that means it could be lemon or lime. So there's a total of 17 seeds there. So 17 out of 25. And then we assume we get one of those, so it's 16 out of 24. And we assume we planted another one, and so it's 15 out of 23. And when we multiply this together, we get 34 out of 115, which is about 29.6%. So looking at this, we can see that the probability of getting no orange trees is pretty big. So if you really want an orange tree, it's going to be a little bit harder to get that. If you want all 3 orange trees, you're only going to have about a 2.4% chance there. So wrapping it up, which formula to use? So if you want to use the OR formula, OR problems will almost always contain the word OR in the statement of the problem. So an example, find the probability of selecting a heart or a 6. OR problems will generally involve only one selection. So one card is selected or one die is rolled. And it's in the events where we can have both happen at the same time. So the AND formula. AND problems will often not use the word AND in the statement of the problem. So an example, it says find the probability that both cards selected are red. So we didn't use the word AND, but this would tell us AND. Find the probability that none of those selected is a banana. And AND problems will generally involve more than one selection. So there's going to be multiple trials in that 2 cards are selected or 3 coins are flipped. Alright, so that is compound probability and using the words OR and AND.